talk today, and we'll learn about bars in a very interesting type of galaxy that we don't know much about. So take it away, Wes.
Awesome. Thank you so much. Thank you, everyone, for being here for round 2 of the magical, musical room game we played starting yesterday. Sorry for the email spam, but we finally have a room. We have a projector that works, so everything is good. So thank you all for being here. I'm excited to talk with you today about all the research I've accomplished towards my dissertation on characterizing bars in low surface brightness galaxies. Thank you, Mike. So before beginning, of course, there's a number of people that I would like to thank. First and foremost, of course, my advisor, Dr. Rachel Cusier de Nere. All of her help and advice these past few years. Without her, this wouldn't be possible. And for nudging me along the directions of looking at LSBs in general for these very cool objects. As well, I'd like to thank my thesis committee, Dr. Misty Bentz, Dr. Mike Crenshaw here at Georgia State Astronomy, Dr. Megan Connors here at Georgia State Physics, and joining us from Skype, we have Stacy McGaugh from Case Western Reserve University. Hi, Stacy. Next, of course, I have to thank my family, my parents who are here, my fiance, her mom are here as well. All your guys' years of support, couldn't have done this without you guys. And finally, of course, my friends here at Georgia State, especially the incoming class of 2014. So with that, I'd like to jump into the motivation and goals for my thesis project. Galaxies are huge conglomerations of stars and gas and dark matter and all that stuff. But more importantly, they are one of the most important tools we have for understanding our current universe, the formation and evolution of our universe. When we look out, we see that they come in a wide range of properties. They look different from each other. We call that the morphology of the galaxy. So in the early 20th century, Edwin Hubble was one of the first people to really sort of quantify or characterize this morphology. And he came up with the now famous Hubble diagram, or the so-called Hubble tuning fork diagram, where he, by and large, grouped galaxies into 2 big groups, ellipticals and spirals. Now, he believed that ellipticals, these spherical groups of older stars, that we now know are older stars, but he thought that these were the early stages of galaxy evolution, and that they sort of progressed into later type spiral galaxies. We know that's not really the case nowadays, but the nomenclature has stuck, and ellipticals are called early type, and spirals are called late type galaxies. Furthermore, he broke up spirals into 2 groups, sort of spirals and barred spirals, because barred spiral galaxies, he saw enough of them to sort of distinguish them, giving us the tuning fork. So with these galaxies, we can look at how they differ from each other, we can group them up based on how they appear, and we can hope to sort of learn about the universe as a whole based on the morphology. I will be focusing more on the spiral galaxy side today, so it would be nice to know what it really is. We heard a little bit yesterday from Book Young about our own spiral galaxy, the Milky Way. And here's an image of our closest neighbor, Andromeda, which happens to be a spiral galaxy. So when we see a spiral galaxy, we see a disk of stars and gas orbiting around the center. We can see also these dust lanes that are tracing out the spiral structure itself. So the dust is blocking the light from the disk itself. The disk that we see is actually much wider than it is tall. So the scale height of these disks is basically, in a sense, negligible compared to how long they are in radius. Spirals are also host to these central components. It could be a bulge or a bar. These are host to more older populations of stars. And these 2 sort of disk and bulge / bar, pretty much how they interact is an ongoing area of interest. And of course, around this is thought to believe, we believe is a sort of very massive dark matter halo. And so the morphology that we're interested in is the sort of interaction and distribution of these 3 properties for spiral galaxies as a whole. Now, it sort of may look like it, but there's probably just a bulge inside the center of Andromeda. But remember that this group of spirals down here, these barred spirals, Edwin Hubble broke off. That's because we now know about 60% of spiral galaxies are host to bars. So these are very important features that we need to understand. So they're basically just groups of stars that look like a bar in the sky, but you can also see that the arms of these spiral galaxies form at the ends of the bar themselves. Now, bars are very important for sort of secular evolutionary processes. That just means sort of evolutionary processes within the galaxy itself, outside of, say, an interaction or the environment of the galaxy. And this could be things like feeding of the active galactic nuclei in the center, the formation and regulation of the spiral arm structure in the galaxy, as well as angular momentum transfer between the disk and the dark matter halo itself. So characterizing these bars is a very important tool for us for understanding the evolution of galaxies as a whole. And this is usually done with three properties: the length, the strength, and the pattern speed. So the length, while it may seem straightforward, how far a bar extends into the disk, if you look at these various images of barred galaxies, you can see that the bars themselves are rather unique to each galaxy. Sometimes there's even internal structure. There could be maybe a second bar in some of these on the inside, so measuring the length isn't as always straightforward as it seems. The strength was originally a visual parameter, so one would look at an image of a galaxy and say, that's a strong bar, or that's a weak bar. And so it's basically just, that looks like a strong bar, it's really big, and that's a weak bar, it's kind of small. Nowadays we do characterize this, we quantify it, and it's more a reflection of the sort of gravitational potential of the bar itself. Lastly, the pattern speed is the sort of dynamical aspect of the bar. That's the angular rotation of the bar. And by measuring this, one can sort of learn more about if there's been an interaction with the dark matter halo, any angular momentum transfer with the disk, a lot of interesting things. So we seem to have a good handle on the morphology of galaxies, but there's a very important caveat. Namely, when we look and observe galaxies, it depends on two things: the brightness of the galaxy itself and the brightness of our sky. So that might seem like an obvious statement, but it has sort of a dramatic consequence. Namely, that we discovered that as we looked at galaxies closer and closer in brightness to the sky level, the number of galaxies fell off. So we were seeing basically that all galaxies were brighter than the sky. So either the universe knew how bright our sky was and was only forming galaxies brighter than the sky, or there happens to be a number of galaxies that are at that level or even fainter. And as it turns out, that is exactly true. So a low surface brightness galaxy is a galaxy usually defined as having a central surface brightness fainter than 22.5 in the B band. So these are very faint objects, but as it turns out, they make up more than half of the galaxy population as a whole. And we're not talking about little tiny dwarf galaxies or spheroidal or things like that. These are real massive late type spiral disk galaxies. For example, this is NGC 45 and LSB, relatively nearby. And we can see for this galaxy, it has a disk as well, but it's mostly gas. It doesn't have a lot of stars in there. And it also doesn't have a bulge component, and this galaxy doesn't have a bar either. You can also see that it is quite blue. So once we realized this, we began to learn more and more about this LSB population as a whole, and we found out that they're, in a sense, relatively unevolved systems. They have low star formation rates, they have low metallicities, they have huge reservoirs of neutral hydrogen. Again, they have unevolved, they're just sort of sitting there gas. And more interestingly, they're basically dark matter dominated at all radii. So this is different from our sort of normal galaxy we think of. So if we go back and we think of Andromeda or perhaps the Milky Way as a normal galaxy, that's not necessarily the case. This could, in a sense, be a normal galaxy, and we're used to looking at the sort of oddballs, in a sense. To give you another comparison, because Andromeda is very close to us, it's not fair to compare that with NGC 45. These are two composite images of two galaxies, one an LSB on the left and an HSB on the right. I picked these two because they are about the same size on the sky, about 12 to 13 arc minutes. But the HSB is about 5 magnitudes brighter than our LSB, despite it being twice the distance away. And this happens to be one of the nearest LSBs to us. It's also host to the, I think, the currently smallest Seyfert 1 in it. Yes. So very cool object. But this is sort of to give you an idea of what we're dealing with. The two LSBs that I've showed you didn't have really a bulge or a bar, and that's for sort of two reasons. So LSBs are gas dominated and they're also dark matter dominated. So both of these are thought to work against the formation of bars in general, and we do find that only about 20% of LSBs are host to bars. So compare that earlier, normal galaxies, we think of about 60% of them. Now, in the early 90s and so, this was about 4 to 8%. So we are, as we find more and more LSBs, we are finding that the bar fraction increases, not as if that's happening right now. We're just finding more barred galaxies. But that still is much lower than 60%. So again, that's because dark matter, a dense dark matter halo and high gas content is going to suppress both the formation as well as the growth. So if you're going to form one, it's going to be very short, very small, and very weak. And it's also going to be rotating very slowly. At least that's what's expected. This is UGC 628, which is a barred LSB. You can see the bar there and the spiral arms coming off. This is again, a 3-color Sloan image. This galaxy here is the only LSB that has a pattern speed measurement. Remember, that's that dynamical property that's important. Things like length and strength are sort of measured for LSBs, but there's only one pattern speed measurement. So in a sense, these sort of galaxies are asking to be placed into context with HSBs. Because if we want to understand the galaxy population as a whole, and we think we do, we actually need to understand LSBs to make sure that we know about galaxy as a whole. So with that, we come to the first goal of my project. It's simply to characterize those 3 bar properties for bars in LSBs. As a reminder, that's the length, the strength, and the pattern speed. Except not really, because the pattern speed turns out to be an extremely difficult thing to measure. It requires a lot of high-quality spectroscopy and as well as high-quality photometry. And to do this for LSBs almost becomes prohibitively difficult, and it's also prone to very high errors. So instead of this, we're going to be measuring what's called the co-rotation radius of the bar. So the co-rotation radius is the radius in a galaxy disk where orbits are equal to the pattern speed. And we care about this because we can actually characterize the pattern speed by this ratio of the co-rotation radius to the bar length. Theoretically, for high surface brightness galaxies, it occurs very close to the end of the bar. And we can call a bar fast or slow based on how it's rotating based on this fraction. So if this relative bar pattern speed is less than 1.4, you have a fast bar. And if it's greater, you have a slow bar. For our HSBs, or high surface brightness galaxies, almost all of them are host to fast bars, as expected. Another way of saying it, they haven't experienced any slowdown due to dynamical friction from the dark matter halos. The converse for LSBs is unknown. It's expected for them to have slow bars since they have a lot of gas and a lot of dark matter, but we simply don't know. So that is goal number 1 of the project. Goal number 2 is to obtain photometry for barred LSBs. As it turns out, a good deal of barred LSBs simply don't have any photometry available, so we need to characterize their brightness and things like that. We also wish to obtain stellar and gas mass estimates for our barred LSBs as a whole. And finally, we want to put all this into context with bars in high surface brightness galaxies. Does there exist a continuum across surface brightness, say? Okay, so with that, we'll go over the approach of how we tackled these goals. We opted for a photometric approach. Again, that's because that pattern speed measurement is extremely difficult to obtain. So with B and I band images that we took on the Arctic imager at the 3.5 meter telescope at APL, there it is, we can measure all 3 of those bar properties for a large sample of galaxies. For gas masses, if available, we can obtain H1 fluxes, which we can convert into a H1 mass and convert that into a gas mass. And finally, there exists ample data for HSBs out in the literature. So if we find an HSB sample, we can obtain Sloan images in order to perform analysis. Now for our LSB sample, we broke it up into 2 studies. Our first one, we focused on 4 well-studied LSBs that happened to be host to bars. One of them is this UGC 628 again. And I'm showing here a comparison between the available Sloan data, the 3-color image, to our Arctic image. So you should be able to see that we go much deeper and our resolution is much better than the available Sloan data. So this allows us to probe the disk structure better, but more importantly, we can characterize that bar much more easily than in that image up there. Our second study, we perused 2 sort of very large LSB surveys, and we visually identified additional barred LSBs for study. We were able to obtain photometry for 11 of these galaxies shown here. We have a B and I band image for each of these galaxies. And again, we can see a lot of varied morphology. Some of them have clear spiral structure. Some of them are rather small on the sky. Some of them have a rough disk at best. So we're probing a wide range of morphologies in our sample. So in total, we have a sample of 15 barred LSBs that we obtained BNI band images for. Just to sort of hammer in again the importance of our data, these are 3 additional composite images of 3 galaxies in our sample from Sloan. You can see that they're barred, but especially this one, first of all, that's a small bar, and if you want to do analysis on that, that's going to be quite challenging. The spiral arms themselves are sort of lost, and you can't really see the disk. So with our Arctic images, you can see these arms much more clearly. It's clearly blue. We're seeing the disk much better, but more importantly, we're seeing the bar much better in each one of these images. This bar is small, sure, but it is much better than, say, that. So now that we have a sample and we have our data, I'll go over the methods we use to measure the bar properties of our sample. We'll really go into the results from these methods once we talk about comparing them with HSBs in general later on. The bar length turns out to be the most important of the 3 parameters. The strength and the co-rotation radius both depend on the bar length. So you should really nail down your bar length as best as you can. To do this, we used 3 widely used methods from the literature. 2 of them involve fitting isophotes to your galaxy image. So concentric ellipses of varying eccentricity and position angle. This allows you to study the structure in the galaxy as a function of radius. So in the top, we're seeing eccentricity as a function of radius, and in the bottom, we're seeing position angle as a function of radius. So again, these are just those ellipses you're fitting on the sky, and how squished they are, and how they're oriented on the sky. In the top, the bar length measure is simply the radius of maximum eccentricity, or the most squished points on that profile. So if you think about a bar, again, that's just that elongated feature, so that sort of makes sense. And on position angle, a bar is a constant feature on the sky, so its position angle isn't really going to change. Once it does, it usually changes dramatically, and we can take that to be the end of the bar. If you can see, these vertical dashed lines show the bar length, and they're about the same, between 3 and 4 arc seconds. We use an additional literature method, which involves decomposing the image with a Fourier series. And by looking at the even modes, because if you think about going around the image, the bar shows up twice azimuthally. It's strong, therefore, in the even modes. And this sort of region is called the bar region, based on that method. And right there, again, it's about 3.5. So all 3 of these methods roughly agree for a random galaxy in our sample. We also develop and use a new method for measuring the bar length, which uses what are called azimuthal light profiles. So what are those? Generally, when we think about a light profile of a galaxy, we're just sort of starting in the center and moving out radially with the average light as a function of radius. An azimuthal light profile doesn't make any such averaging. It takes a deprojected galaxy image, so that simply takes your on-sky image, manipulates it so it looks like a circle on the sky. And we then fit radial divisions and azimuthal or angular divisions. So by keeping these bins as small as possible, you can get an average light per radii per angle, and it looks something like this. So these are the azimuthal light profiles on the right, and I've roughly color-coded them with the rings on the left. So for example, if we look at that left red ring, you can imagine going around the ring, seeing an increase in light reflected by a hump in this profile. It gets faint again, dips down, and we see another hump right here. You can imagine going out radially in this image and doing the same thing as we do here until you get out until the disk. Again, this is sort of a rough comparison, where now the humps have sort of moved around and they've gotten fainter as well. This is because we're no longer tracing the bar with these azimuthal light profiles, and we could be tracing the spiral arms of the galaxy itself. So by tracing these hump locations, we can then get a handle on the bar length. So here are 4 random galaxies from our sample with the 4 measures over plotted that deprojected image. So if you get a measurement, it's not really a good idea to just blindly use what your routine is saying. It's probably a good idea to check if your routine has found the bar length. So each of these 4 lines represents a different bar length measure. So you should be able to see the bar as this clearly straight dark feature in the image that we're trying to get the length of. Our two isophoto methods are the green and yellow lines. Our Fourier is the red line, and the azimuthal is the blue line. What we find is that the literature methods that are most typically used tend to be very inconsistent for low surface brightness galaxies. And this could be because, well, LSBs are low surface brightness, so their disks are somewhat hard to nail down, and these routines tend to not have a good time with. Instead, what we find is this blue circle for the azimuthal performs the best for, in a sense, a rough disk, clear spiral arms, rough spiral arms, and sort of no spiral arms. So by finding the bar length with the azimuthal method, we find the most consistency and the most accuracy. But since it's so important, we really need to make sure that the bar lengths we're measuring are actually the true bar lengths, or at least the most accurate. So how can we do that? We opted to generate fake galaxy images. So we simply generate an image that consists of a Sirsic disk, that's just an exponential disk, and a bar component, its intensity is given by the Slovy equation. By randomizing these parameters, sort of the position angle, inclination of the galaxy, the bar length, maybe a scene parameter, we convolve it with an equation to mimic seeing parameters, adds in some random noise, things like that. We're sort of making fake galaxy images. We don't have any spiral arms in these images or holes in the disk or things like that. So we're really giving an idealized scenario for each one of these methods to find the bar length. And what we find is that two of our methods outright fail for a given, for even a fake image, and two perform rather well. That radius of maximum ellipticity, so this is the measured bar length as a function of true bar length, these two here quite clearly underpredict the bar length rather significantly. So this is a known result from people who have done such a modeling beforehand. But we find that radius of position angle does a little well. If it's a perfect, it's going to fall on that line of unity, and the dashed line is just a fit to our data. And our azimuthal method performs rather well as well. They sort of fail at longer bar lengths, but we also don't have as many bars that are greater than 10 or 12 arc seconds. Now, even though the position angle method does fairly well on fake images, we already know that it doesn't do well on real images. So it might work in an idealized case, but we know it fails for real galaxies. And we know that our azimuthal method works well both on real images based on just looking at where they are, as well as on idealized images. So we're going to be using this bar length measure for all of our galaxies from here on out. Again, we're really going to go over the results from these bar length measures later in the talk, but we do find that bars and LSBs are rather short, typically not exceeding 2 or 2.5 kiloparsecs in length. And that number is probably not going to mean anything until we get later on in the talk. But with that bar length, we can now move on to the other parameters. The bar strength, again, is quantifying what was a visual parameter. So by looking at these sort of different galaxy images, ranging from not barred to very barred over here, we can see as you move, you should be able to see a bar becomes more and more pronounced visually. It becomes sort of clear here, better, and that's a strong bar. You sort of just like know that visually. But what does that even mean? So nowadays, there are many methods, but we opted to use a decomposition of our azimuthal light profiles to characterize the bar strength itself. And again, we'll go over that in relation to HSBs later on. But we do find that bars and LSBs are rather weak. So the more interesting measurement is now we can actually do this co-rotation radius business with a bar length. So again, we use the decomposition of our azimuthal light profiles, and based on spiral density wave theory, you can look at intersections between a blue band and a red band, as these are probing different stellar populations in your galaxy. An intersection of these phase profiles indicates a radius of co-rotation. So that's an important bit to note, because a bar could have multiple, and a disk can have multiple radii of co-rotation. So to counter this, what's typically done is the first radius after the bar length is taken to be the co-rotation radius of the bar. That's important because for this galaxy here, UGC 628, if you remember, this galaxy has a pattern speed measurement that does exist, and it's found to have a very slow bar. its relative bar pattern speed is about 2 or something like that, and the separator is about 1.4. That's a very slow bar. If you extend this plot out to very far radii, there's an intersection way over here around 30 arc seconds. So if you were to say measure a bar that's 15 or 16 arc seconds in length, then that can't be your radius of rotation. You have to use the radius out at 30. So you'd get a pattern speed of about 2 or so, a slow bar. However, literature works have used the previous sort of methods, like that radius of maximum eccentricity, etc., which we've just showed are not exactly trustworthy for LSBs. When we use our azimuthal method and we visually plot the bar length on the image, we find the bar is actually closer to 12 or 13 arc seconds. That means then that we have, 15 over 12, we have a fast bar in a low surface brightness galaxy. And not only just for that, for our initial study, we found that 3 out of 4 LSBs were host to fast bars. High surface brightness galaxies are expected and known to, by and large, have fast bars, but LSBs are expected to have slow bars because they're supposed to be slowed down by their dark matter halos from dynamical friction. Instead, we find only one has a very slow bar up here. When we extend this to our second study of the total 15 LSBs, we find almost all low surface brightness galaxies are host to fast bars, except for this one way up here around 2.5. That's F563V2, and that's its Sloan image right there. So again, you can see not very high quality or deep imaging we're working with the Sloan. It's thought that maybe a galaxy experiencing an interaction would be host to a slow bar. But LSBs are known to be very isolated galaxies, and F563V2 has no known companion. So as it looks, LSBs are host to fast bars, and that this one is not the norm. As expected, it's the oddball in this bunch. So now that we have the bar properties of our low surface brightness galaxies, we can now probe or assemble a sample of HSBs to see how bar properties change as a function of surface brightness. To do that, we assembled a sample of 24 HSBs from 2 very large representative surveys. And to make sure that they are in fact HSBs, there are transformation equations from the Sloan system to the Johnson system, so we can see what the central surface brightness is for these galaxies. 2 of our, it was originally 26. 2 of the ones we picked actually happened to be LSBs, so we added 2 additional ones for our analysis. These all have existing bar length measures that we can compare our results with, and a few of them have existing relative bar pattern speed measurements that we can compare with. And again, since these are HSBs, the Sloan images are of high enough quality, and we can use G and I band images to perform our analysis. Now, G and I are not the same as Johnson B and I. They're roughly around the same wavelength range, but using different bands than B and I has been done in the literature, and it does give similar results. So we apply our same techniques that we just talked about to high surface brightness galaxies to obtain the length, the strength, and the relative bar pattern speed. In this histogram up here, this is a normalized bar length, so the bar length divided by the disk scale length. This is because LSBs and HSBs don't necessarily have the same physical size. So by comparing the bar length, to how big the galaxy disk is in a sense, is a much better sort of comparison. We find that our LSBs, the blue histogram, have lengths that are roughly around the order of their disk scale length, whereas HSBs are closer to 2. So 2 different sort of populations of bar lengths. The same is true for bar strength, where bars and LSBs tend to have strengths only about 0.2 or so, where HSBs are around 0.4 or even greater. So again, this is expected. If you're going to form a bar in an LSB, it's expected to be short and weak. However, we find, in a sense, nothing, there's no trends with the relative bar pattern speed measurement. So if we fill in this relative bar pattern speed as a function of bar strength from earlier, if these weren't color-coded, you wouldn't be able to differentiate an HSB from an LSB. Finding slow bars here in HSBs. That's not uncommon. You do find a couple. It's usually about 75% or even more of HSBs are host to fast bars. So this is consistent with previous findings. We do find, though, that there sort of is a continuum, at least in bar strength, that bars and LSBs tend to be weaker than those in HSBs. So now that we have bar properties, we'd also like to obtain masses to see if there's any trends with mass. To do that, we use Sloan available photometry, so this is their magnitudes, disk scale lengths, things like that, to convert into the Johnson system outright. This is because V-band mass to light ratios tend to be more accurate and give you less scatter for your stellar mass estimate. So by obtaining a V-band mass to light ratio, we can estimate a V-band luminosity, so we get an estimate on a V-band stellar mass. Again, our gas mass, we can obtain available H1 fluxes, so we're creating a subsample of our total LSB HSB sample, and we can convert that into a gas mass. And this is what we find. So we have the stellar mass in the top left, the gas mass top right, and the total mass in the bottom. This is not the dynamical, this is just the total baryonic mass, so your gas plus stars. We find our barred LSBs are gas dominated, and then our HSBs are stellar dominated. Again, this is expected. But we find that our LSBs span a huge range of stellar mass, ranging from 10 to the 6 to roughly 10 to the 10 solar masses, whereas the HSBs are clustered almost exclusively up here at 10 to the 10. It's sort of the flip side for the gas mass, where our LSBs almost are all contained at around 10 to the 9 solar masses for gas mass, and our HSBs have a larger spread. With these gas masses, we'd also like to see if there are trends with bar properties in the so-called gas fraction. So how dominated is this galaxy by gas or stars? So here, this is an important parameter to look at, but we're also interested in the gas to stellar ratio. And I'm sorry, Todd, with this log plot. But it is helpful because at 0 here, this is in a sense roughly unity stars to gas mass in the galaxy. What we find is that almost all of our LSBs have positive values, meaning they are dominated by gas, whereas our HSBs are almost entirely dominated by stars. We stress that selecting our samples was based on the photometry available, so how bright the galaxies were. If a galaxy has brightness brighter or fainter than a value, it's an HSB or an LSB. This, in a sense, is reflecting an underlying property of these two galaxy populations. And finally, this is consistent with the LSB population as a whole, so very gas-dominated objects. So with all of these, we can sort of explore if there's a bar continuum in properties, and we find that length and strength clearly show trends with galaxy properties. This includes with each other. So here's bar length in physical units as a function of bar strength, and this is normalized bar length as a function of bar strength. So while both clearly, trend with each other, the normalized bar length has a much tighter relation than the sort of larger scatter with the physical bar length. Again, we're reflecting that these two galaxy populations are different sized objects. Bar length and strength correlate with Hubble type. So this Hubble type T is just a numerical representation of a galaxy's morphology, which allows us to make plots like this. But we can see that for earlier type, which is a misnomer because these are all spiral galaxies, elliptical galaxies have negative Hubble type. But for early type spirals, you have longer and stronger bars, and it smoothly transitions into shorter and weaker bars. This is also true with stellar mass, with some more significant scatter, especially with strength. But we see that as you move to more stellar-dominated galaxies, you find longer and stronger bars. Again, this is expected, especially since bars are stellar features. It makes sense that a stellar-dominated galaxy might have a stronger or longer bar. Finally, we find that both surface brightness and that sort of gas ratio correlate with bar length and strength. And we're showing both of these together because, in a sense, these are representative of the similar thing. That as you go to brighter galaxies, you go to more stellar-dominated systems. So the same sort of trends are inverse. As you go to brighter galaxies, you get longer galaxies, but as you go to gas-dominated galaxies, you get shorter bars. I hope I'm hammering this in. However, we find that relative bar pattern speed doesn't correlate with any galaxy property. Previous results with high surface brightness galaxies show that bars are fast across redshift, Hubble type, mass, etc. But we're now extending this to surface brightness and conversely to the gas content of a galaxy. So this is the currently largest sample of LSBs with relative bar pattern speed measurements, and there is no clear trend with any of these. Bars are fast across surface brightness with a few outliers. In other words, bars in whatever galaxy you're looking at haven't experienced any significant slowdown due to their dark matter halo. Now that's important because either they haven't experienced any slowdown, or we just happen to find when all these bars are forming, and bars tend to form fast. So we're either all finding these bars when they form fast, or it's more representative of an underlying property. So with all these properties, let's try to see if we can find maybe an underlying cause for our results, namely that we find short, weak, but fast bars. So in the current context of galaxy formation and evolution, you have a very massive dark matter halo that imparts some net angular momentum to your big protogalaxy gas ball, right? And as that is imparted, you get the conservation of angular momentum to cause the disk to collapse into, well, a disk. And so you have this spinning disk inside your dark matter halo. And currently, an explanation for a low surface brightness galaxy is that you have a very high spin dark matter halo. It's spinning very rapidly. In a sense, this then spreads out the material in the disk of your galaxy, which then means less star formation, less stars, less brightness. So that is a sort of general idea of how you could form a low surface brightness galaxy. This sort of relation here is what we use to estimate the so-called halo spin itself. And high spin halos also, other than forming an LSB, they also suppress bar formation in general. So this is the bar fraction as a function of halo spin. And we see that for lower halo spins, we see an increase of bar fractions. That's your HSB population. These are slowly spinning halos, so there's no reason that a bar could form and keep growing over time. But as you move to higher spin halos, the bar fraction falls off around to that 20% value, but that the number of short bars increases. So there might not be that many bars, but they are forming short. And the sort of boxed region is in general, depending on who you ask, if this lambda is greater than 0.03 or 0.05. That's sort of where LSBs are thought to form. Now, this could explain why our bars, in addition to the gas content, this could explain why our bars are short and weak. But there's also evidence that a high-spin galactic halo can keep a bar fast over time. That's because if the dark matter halo has a high enough angular momentum, the transfer between the disk and the halo is sort of prevented, or at least sort of mitigated. So a bar cannot be slowed down, which then means it's not going to grow as it slows down over time. So they will be kept short, weak, and fast, possibly. So to test this, we estimated that halo spin parameter, and we indeed found that LSBs occupy this high spin regime. For as you go to increased halo spin, you find shorter and weaker bars. I keep almost saying that, we do not find a relation between halo spin and relative bar pattern speed, which in the current context possibly then makes sense. Again, for the high spin halo, you are, in a sense, keeping the bar fast over time. The only, in a sense, other explanation is, again, we happen to be finding all these galaxies the second after they formed, which is extremely unlikely. To sort of see if there's an underlying explanation, hopefully you remembered that the gas content and the surface brightness tended to go hand in hand. When we see if there's a relation between surface brightness, gas content, and halo spin, we find that's the case. So as you go to higher spin halos, you find fainter galaxies, and there's a significant scatter, but you do find more gas content. So it appears as that this halo spin parameter could be a reason for the short, weak, and fast nature of the bars. Now that's a pretty important and sort of big takeaway from this, but there's still a lot to be done from our results. Namely, we could keep obtaining relative bar pattern speed measurements, but only one galaxy actually has that physical pattern speed measurement. So physically obtaining that dynamic property could shed further light. Namely, this relative bar pattern speed measurement is just a ratio of two other properties. Theoretically, those two properties could have evolved to conspire to keep a bar fast. So a bar could have grown longer faster than its rotation radius propagates outward, so a bar could still look fast, even though it might be rotating more slowly. In order to do that, you would then need to apply that challenging method, and you would need either long slit data or large scale like IFU surveys. And I'm going to focus now on these sort of large scale surveys because things like Manga and Khalifa are providing high quality data for thousands and thousands of galaxies. So if we can use maybe Manga, we could in a sense obtain pattern speed measurements for a large number of LSBs. So Manga, that stands for Mapping Nearby Galaxies at APO survey. It's a very ambitious project, which basically is looking at the Sloan sky and is obtaining thousands and thousands of IFU fields for all these galaxies. So just very quickly, an IFU, an integrated field unit, has all these fibers which you're obtaining the spectra at. So you have your sort of galaxy as a function of wavelength in all these different regimes. So you can obtain then high quality velocity maps, say, or metallicity maps with these IFUs. However, there's a very important caveat about the Manga sample, namely, it selects galaxies with stellar masses greater than 10 to the 9. If you were paying attention earlier, sparred LSBs had stellar masses usually lower than this, from 10 to the 6 to 10 to the 10. So this right away eliminates probably half of our sample. Well, how bad is that for LSBs in general? So since this is Sloan data, we can estimate B-band central surface brightnesses and see how many LSBs are present. We can also exclusively select for disk galaxies and bulgeless galaxies because LSBs are not host to bulges. What we find is that out of the 1,500 disk galaxies, there's only 29 LSBs. And this is a histogram of the estimated central surface brightnesses for the sample. And you can see that Manga is clearly biased towards your high surface brightness galaxy. So it is, in that sense, it's not representative. That vertical line separates HSB and LSB. Well, what about bars in Manga? Maybe there's only a handful, but maybe we could use this data. Again, if we sort of correlate or reference that with the Galaxy Zoo catalog, we can insist on a bar fraction weight. If we do that, however, there are 8 barred LSBs out of the total 1,500 disk galaxies. And if we want to maybe do something with that data and insist that it's good quality, there's 4 in Manga. This is just showing that a proposed sample would be very blue. So LSBs come in blue and red colors. So this is a color-color diagram. This vertical line separates there's a literature separation between blue and red LSBs, and almost all of the LSBs in Manga are blue. So these are very stellar heavy and blue barred LSBs, not very representative. But there are 4, and here they are. So for each one of these, we have the on-sky image, the Sloan sky, with the IFU field overplotted. So you can see, yeah, these are barred galaxies. And the image quality isn't the best. So yeah, these are LSBs. We also show the stellar velocity and the H-alpha velocity maps. So these are color-coded dependent on the redshift, blue shift of either your stellar absorption features or your emission lines. So for a rotating disk, you should see nice, clear rotation. And we do, for the most part, not necessarily sure what's going on in this stellar velocity map here. Now, if we were to obtain pattern speed measurements with these galaxies, sure, we would increase the pattern speed measurement up to 5 from the previous 1. That's good, but you're not going to learn any real meaningful statistics or information about the galaxy pattern speed population as a whole. You actually would need a much larger sample, and things like MANGA are not adequate enough to provide you with such a sample. What that means is you would need a sort of dedicated IFU survey to obtain LSB measurements, which is no easy task. So with that, I'd like to wrap up with a summary of all the work I've accomplished. I successfully measured the bar properties of 15 barred LSBs. That's obtaining the length, the strength, and the co-rotation radius. And this currently constitutes the largest sample of relative bar pattern speed measurements for bars and LSBs. Finding 13 out of 15 are fast. Again, this is sort of contrary to what's expected. They're expected to have slow bars. We successfully obtained mass estimates for 10 of our barred LSBs. In estimating a V-band luminosity and available H1 fluxes, we get those stellar and gas masses. We find that the barred LSB population is just as gas-rich as your LSB population as a whole. And when we put these in the context with high surface brightness galaxies, we find that there exists a bar continuum between HSBs and LSBs, with longer and stronger bars found in earlier type spiral galaxies as expected, but that no such relation with surface brightness exists for relative bar pattern speed. So we've now put our little brick in the wall saying that bars are fast across surface brightness, now going with Hubble type, redshift, mass, etc. Lastly, the kinematics of barred LSBs still remains relatively unknown. So obtaining pattern speed measurements, rotation curves, mass decompositions, and such is the next step for this. Now, large-scale surveys like MANGA, using estimations on the brightness of the sample, are heavily biased against LSBs, and you're not going to obtain a large enough sample, meaning likely would need to develop or begin observations independently to obtain IFU for LSBs in general. And with that, thank you very much. Yeah.
I got a question that. So, you said that dark matter.
Mm-hmm.
And then you said that dark matter seems to faster rotation speed LSBs versus HS.
Possibly. In order to do something like that, however, you would really need to get rotation curves. So with that, you can decompose it into all the various components, and this is typically how we see that LSBs are dominated at all radii. So if you look at rotation as a function of radius, for a high surface brightness galaxy, this solid line is your rotation, and this dashed line is your sort of baryonic star component. This one is your dark matter, and so you don't really need dark matter at all. LSBs, on the other hand, in the current paradigm, Todd, in the current paradigm, LSBs is the opposite. You need that all the way down in the beginning to explain the observations. So to see, in a sense, about bars and the halo spin, you would need to do something like that to learn more about the halo itself. The theoretical possible halo, Todd. Todd.
You knew it was coming. So, I think I missed it. How did you measure your halo speed?
Yes. In the interest of time, I sort of went over that. So this is the original sort of equation with your angular momentum, your energy, your mass, all that stuff. There exists a simplification estimation which uses the disk scale length and the flat portion of a galaxy's rotation curve. It's an estimate, yes. Again, to get the actual physical one, you would need more in-depth, kinematic observations.
And so, Bars are spinning too fast.
Sure, yes.
Faster than you expected.
Right.
Which is really cool.
Yes.
Opposite of what you expected.
Right.
One explanation is that the
Well, in a sense, if you have a static halo, then that's like a perfect sink.
right.
So you can keep dumping it in, which allows the bar to grow and slow down. For a high spin, then you can't dump the angular momentum as well, so it stays fast.
So my question is, why do you need to explain?
There could exist other things, possibly like MOND, to deal with this. I don't believe that there is a more formal workaround for that. This is sort of done in the current paradigm context. So I think the interesting part is that the fast bars are going contrary to what the paradigm expects. That sure, they might be high spin, but the amount of dark matter within the LSBs in general, especially the inner regions where the bar exists, should in a sense slow down the bars over time. Or we found all bars once they formed, right? Which isn't likely. So I think,
Keep going.
oh yeah, I think more than,
One more little thing.
Yeah.
If there is dark matter, what is it?
we don't know.
Are going fast,
Right,
like you expect.
yes. So because if you have the dark matter present, especially in the inner regions, then through dynamical interactions, it's transferring angular momentum to the halo, and so it should grow and slow down over time. Well, theoretically, it's a big, giant halo, right? So you're imparting momentum into it, but if that would actually speed it up or not, in the grand scheme of things.
First question. It's more,
Mhm.
let's say the gas. Let's say there's star. Will that star formation, or let's say star form, will
So
it go other way around?
I flew by it earlier as well, but there's a long outstanding problem in this sort of field that's called the cusp core problem. So simulations predict a very, very dense dark matter halo in the center, but we actually observe not that. It's a flat distribution and there's that conflict, the cusp core. Theoretically, if you have stellar formation ongoing or AGN or what have you, AGN don't really form in LSBs, so it would have to be stars. It could push it out, but that in a sense comes with this whole suite of other problems. But theoretically, sure, if you have a significant formation itself, it could alter the profile. Elliot. I mean, I would say no because I really think this is interesting. But so another important thing is that there's only 4 present here, right? But someone should still work on this. And because if this data is high enough quality to obtain a reasonable measurement, then now you already know what specifications you need. So you could go better, or you can find something that works just as well. It's just, as it stands, they're just not observed, period, in the surveys. Khalifa has even less galaxies than Manga, which is why I picked Manga. You wouldn't need an infinite amount of time. It would be difficult, but